That's the top view. You're looking down. You're like a bird. You're looking right down in the water. There's a bug sitting there. And this is a lake that's perfectly smooth. But now what the bug starts to do is the bug starts to jiggle up and down. And when that bug jiggles up and down, that bug is a vibration, yeah? And that's vibrating on a nice surface, yeah? We're going to make what begin with a W?
Ripples.
All right. We're going to make waves, gang. We're going to make waves, okay? And the waves kind of look like this. Where I draw the line, that represents like the crest of a wave, like it might sort of be like this. You kind of see what I'm saying? Okay, so this represents the crest of the waves. And the waves go out in all directions. And the fact that they're circles is kind of evidence that they go out in all directions at the same speed. Isn't that true? Like if it went faster over here, then the wave would sort of be like that, yeah? Okay. So the circles are evidence of the same speed. Okay. Now, what would be the frequency of the waves compared to the frequency of the vibrating bug? In other words, if you put your hand here, blip, 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 the waves would hit your hand, yeah? Certain frequency. How would that blip, blip, blip compared to the whoop, whoop, whoop of the bug?
Same.
Same. Isn't that right? The frequency of a wave is the same as the frequency of the vibrating source. Makes sense, doesn't it? Let's suppose now that the bug swims in this direction. What the bug is going to do is the bug is going to swim in the direction of the waves that it's producing. And it continues to vibrate a little bit, yeah? Wouldn't the wave pattern look something like this? Can you kind of be seeing that? In fact, what direction would the bugs be swimming, gang? I mean, you can tell it's going that way, right? Well, the bug might be at rest and the water's going this way. I mean, motion is relative anyway, yeah? Okay. Now, if I put my hand over here, would I get a higher speed wave, a lower speed wave, or the same speed wave? Check your neighbor. And make sure you're listening to the question that's being asked. How many people say, hey, the speed of the wave is going to be the same? Yeah, that's right. The speed of the wave doesn't change. What does change, gang? How frequently that wave encounters you is different, yeah? So I can get a different frequency. When I put my hand here, higher frequency or lower? Can you see it? Blip, 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 blip. Over here. Bloop, 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 bloop. That change in frequency due to motion of the source or the receiver is what we call the, named after a person. Okay, good. It is called it's a Doppler effect. That's right. The Doppler effect is the change of frequency when something moves toward you, away from you, that sort of thing. The change of frequency due to motion. Doppler effect. Let's suppose the bug swims faster and faster. Another bug generates waves that are sort of like this. I got a question for you, gang. How fast is that bug swimming compared to wave speed?
Same.
What do you say? Same. Isn't that right? The bug is going as fast as the waves it produces. Now you say to the bug, hey, Mr. Bug, go a little faster, honey. And the bug goes, man, that bug has got a big problem. Because what's in front of the bug? All the waves the bug has generated in the forward direction are all piled up. That's constructive interference. When we talked about interference last time, constructive interference. And so it's all piled up in front there, huh? And so the bug finds it very, very difficult to go faster. Come on, bug, go fast. Bug said, I can't go faster. There's a wave barrier here. Do you see what the wave barrier is, gang? But that bug can go fast. That bug, right down the other side, and man, smooth sailing. So the bug can break through that barrier. And when the bug does that, you see we get something like this? Now the bug is swimming out in front of the waves it produces, and here's the bug right here. The bug says, hey, honey, smooth sailing. And you know what? You see where these waves overlap here, 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 here? They don't overlap here, here, here. But notice right along the edges, where they all overlap, we get a V. You've watched bugs swimming through the water. You've watched ducks swimming through the water. You've watched birds swim. You've watched boats go. And you always notice the V shape behind, yeah? And you've always said, gee, I wonder what they make in the V wave. And now you know the answer. And that V wave is a superposition of a whole lot of circles that all gang together on the edge and give you constructive interference out here, and there you go. Ain't that nice? This we call a bow wave, usually made by the bow of a boat. But you know what, gang? These ideas apply to sound. Because in the case of an aircraft going faster than the speed of sound, it's going to leave a conical shaped wave behind. And that's called a shock wave. So anything that moves faster than the speed of sound is going to have the sound all gang up and form that high pressure cone. This is really high pressure air. Just like with water, it would be a high wave, yeah? And that high pressure air, when that's you encounter that down below, let's suppose this is an aircraft now, not a bug. Person up here says, hey, wow, look at the aircraft, man, silent. No sound at all. Hey, they finally made it. No, boom! See? And this thing here finally got washed right over. And when that hits the listener can't tell the difference between that and like dynamite going off. I used to prospect in Colorado. It would be way out in the mountains, and sometime we'd hear, hey, is that someone prospecting, someone nearby, someone making some dynamite holes? And we didn't know. And we thought, there it is, military aircraft. But you couldn't tell. We couldn't tell the difference between dynamite going off and a sonic boom. Because when this wave makes incident with your ear, that high pressure air, whoom, just like dynamite, boom, same thing. And you get that loud sound, sonic boom. Produced by what? Incidence of a shock wave. But you know what? There's a misconception going around that a sonic boom is produced by an aircraft just when it punches through the sound barrier. As if going at the speed of sound. You know, when an aircraft goes at the speed of sound, man, that high pressure air is all piled up in front of the wing. And it used to be, way back in the 1940s, they thought an aircraft could never go faster than the speed of sound. Because you're going fast as the speed of sound, man. You've got that high pressure, like a brick wall in front of your wings of your aircraft. You can't get through that high pressure air. Forget it. And lo and behold, it turns out they could get through it. Okay? They could get through. And they entered the whole age of faster than sound aircraft. And when an aircraft is going faster than sound, nice and steady, no opposition. You keep going. And it drags behind that V behind it. If something goes as fast as the speed of sound, we call it Mach 1. If it goes twice the speed of sound, we call it Mach 2. Guess what it's called if it goes 3 times the speed of the sound? Check your neighbor. Mach. Ernest Mach, German physiker of long ago. It's named after him. Mach 1, Mach 2. Let's talk about cars, Mach 1, right? Mach 1 means, man, your car goes 750 miles an hour, or about 340 meters per second. That's fast. Sound travels fast. Not compared to light. About 1/1,000,000th as fast as light. But nevertheless, sound. About 750 miles an hour. So if you're in an aircraft going 600 miles an hour, you don't produce a shock wave. That's because the waves don't pile up in front. I mean, you're traveling along like this, okay? And your waves are sort of like this. See, the waves are still going faster than you're going. It's only as you go as fast as the sound. Of course, then you get like this, okay? And you know what? Those waves don't pile up anywhere but right here. So when an aircraft is going to the speed of sound and a little bit faster, down here they don't get a sonic boom. You only get the sonic boom when it's going appreciably fast enough so that you can generate this shock wave like that. So the misconception is people think that airplanes produce sonic booms going as fast as sound. Not true. Or just going faster than sound. Not true. The sonic boom you hear might have been produced by an airplane that might have cracked the sound barrier an hour ago. And it drags it continuously behind. So that's a misconception. That it's only when the aircraft picks up that extra speed that the sonic boom is made. Not true. All the things with sonic booms you can answer, all the questions that might come up can be answered by considering the analogous, more easily visualized case of a motorboat in the water. You're with your friends, and you're sitting at the water's edge, and you're having your picnic. And we're talking about a river now, okay? And up the river comes a speedboat. And when that speedboat races by, what happens to your lunch that's right at the river's edge? It gets sloshed, right? And when you get sloshed, if someone says, oh, wow, the boat must have just went faster than the speed of the water waves. Is that true or false? That might have happened way, way downrange. That boat's been dragging that V behind it continuously. And people are out in the fields or out in water or whatever, and an aircraft goes by and you get that sonic boom. That sonic boom probably has been dragging behind that aircraft. The shock wave has been dragging behind the aircraft ever since it exceeded the speed of sound. And so like if aircraft go from San Francisco to New York faster than the speed of sound, guess what there's a trail of underneath there? wreckage, honey, wreckage, because that shock wave is going to drag right across the ground and hit everyone underneath there. So you got a chicken coop there that's not built too well, right? All of a sudden, boom! And then it's even worse, because it turns out that the high pressure region is followed by a low pressure region. You ever be water skiing? And you go to the edge and whoop, you come up like that. What's on the other side? Down. It's called, on this side, called the bow wave. You know? Not the bow wave, the tail wave. See? Because you get overlappings of high pressure, and you get overlappings of low pressure. In the case of sound, you get overlappings of pressure, what do you call it, compressions. Where all the compressions overlap, high pressure. Where all the rarefactions overlap, low pressure. And so what you get all of a sudden, boom, high pressure followed by whoop, low pressure. It's sort of like boom, boom. And so it's even more devastating, the sonic boom. Because of rapid high pressure followed by rapid low pressure. Questions?
What effect does it have when the aircraft is flying higher in the atmosphere?
If an aircraft flies higher, what effect would that have on people down below? Well, let me ask you this question. If you're sitting with your friends and the boat comes by and it douses you, what effect would it have if the boat were further offshore and drove by? Less effect or more effect or same? How many say everything's the same? No, it's going to be less. See? You'd be further away. So further away you would have less damage. But then in the case of aircraft, how high can an aircraft go? I mean, aircraft needs air to fly. It's got to hit air. Next time you're driving in a car, put your hand out the window. You put your hand like this. You'll see why aircraft fly. That air hitting the bottom. Now take your hand, go like that, down. Isn't that what you do when you're in the water? You go like this, down, up. Huh? Because that water bounces off that way, push it this way. See? Water bounces off this way, push it that way. Aircraft do the same thing. Yeah. But you got to have the air to ride on. How about the people in the aircraft? People in the aircraft say, what are those people down there complaining about? I don't get any problem. Is that true? People in the aircraft hear the sonic boom too? They're making it. They ought to hear it, yeah? Well, person riding a boat, okay, douses all the kids at the edge of the river. He said, I don't know what everyone's complaining about. Seems nice and smooth to me. It turns out even a bullet, gang, most bullets will travel faster than the speed of sound. So when a bullet goes over your head, what do you hear?
Crack.
A crack. And that crack you hear is what, gang? That's a sonic boom. That's a sonic boom. Okay. Now, what would you hear first? The crack due to the sonic boom or the crack due to the gun going off? Check your neighbor. Okay, gang, what's the answer? What's the answer? How many say, oh, they'd both be the same? How many say, no, you'll hear the bullet fired first, then the bullet moves, so you must hear the firing first, and then you'll hear the crack. Yeah. I'm saying, no, you're going to hear the sonic boom first, and later on, you'll hear things in reverse. And later on, then you'll hear the crack of the bullet. Woo, as strange as it may seem. Yeah. How many say, I don't be knowing?
Lee's going to say, it seems to me it would be the same because you hear the crack of the bullet and then you hear the crack of the bullet. That's what you were saying anyway. So anyway, you were...
hear the crack of the bullet, then you hear the crack of the gun. I'm sorry, Lee. I kind of get SU. Screwed up. How about it, gang? It turns out you will hear the crack of the sonic boom. You'll hear the sonic boom crack, and then you'll hear the explosion of the gun. Ain't that neat? Because it'll get to you first. Hey, how about a circus whip? A circus whip or a person whip, snap, and you get that snap sound? Guess what that snap sound is? MSB. Mini. A mini sonic boom. That's right. When you get that crack, honey, that circus whip is going faster than 750 miles an hour. The tip. And it's making its own little sonic boom. With a towel? Long towel, maybe. A long towel. Snap. Yeah. Neato stuff? Speed of sound about 340 meters per second. But that's in air. And guess what's a poor conductor of sound? Begin with A. Air. The best we got, honey, okay? It turns out like in water, sound travels about 4 times faster. and in steel, about 15 times faster. You know, you kind of make do with that when you have, you get your two ears. Do you ever wonder how is it that someone can make a sound over here and you know it's there? Or here? And you know it's there. How do you know? How do you know where the sound is coming from? How many people have never wondered about things like this before? Okay. But we're wondering about them now, yeah? Huh? It's kind of neat. You know what happens? When a sound is made over here, guess which ear it gets to first? This one. And then this one. So what I have inside here is a computer, okay? And what I do is there, okay? So there, you do that with stereo. Yeah, you really do. You adjust so that you can. You know where you get all fouled up is when you do it under the water. Under the water. You ever play tag with your friends, clicking rocks together? How many people have never done that with their friends? Click rocks together under the water. Okay. You know what you're going to do this weekend out at the bay, yeah? And you click the rocks together and see if you can find out where the rocks are clicking from. It turns out it's very difficult. You know why? Because even if it's over here, it gets to this ear and this ear, almost the same, 4 times the speed of sound gang. You are not equipped for that judgment. A dolphin is. Dolphin got 2 ears. Dolphin knows right. Okay, kind of hard with no neck. But nevertheless, you get the idea. You know about ultrasound, yeah? Ultrasound, high frequency sound. High frequency sound, very, very small wavelengths. And those small wavelengths can discern things. You know about how they send the sound waves into the stomach of a person having a baby or something like that? You don't want to send x-rays, do you? I mean, unless you don't like the kid already. No, you don't want to. You ultrasound waves, really, really neat. These ultrasound go right through, reflect, and give the information. Echoes, huh? The echoes of high-frequency sounds. And guess what maneuvers the same way in the sky at nighttime? Begin with a B, end with at. Bats, right on. Bats do the same thing. How do the bats catch little insects on the fly? They send out beep, 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 beep. The beep hits the insect, bounces off. Beep, beep. Beep. Ah, whoom. Got it. Ain't that nice? Ain't that nice? Picks it up by sonar. Sonar. That means radar echo. Lee.
Why wouldn't lower frequency sounds tell you where the insects go?
A lower frequency, not so good, because a lower frequency is a long wavelength. Remember we talked before about seeing things small with long wavelengths like atoms? You just can't do it. Detail is not picked up. So what the bat does, it makes a chirp that we can't even hear. The chirps we hear are probably the leftover part. In a high frequency, have a small wavelength and can detect small things. It turns out dolphins, too. Dolphins perceive most of their environment with the sense of sound. Because they're way down there, it gets dark, gang, it gets murky, doesn't it? And how's a dolphin get around? In fact, the dolphins kind of got us beat in a little way. Because a dolphin can communicate with others with the same sense that they receive information. We receive most of our information by sight. Huh? Now, how do you give that back to other people in terms of sight? We can't. So we've invented a language. We have letters of the alphabet. We have grammar. We have words. So someone can tell you, boy, did I have a neat time today. The physics that I saw was blah, 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 yeah? And we have a language. And we've always wondered, how come the dolphins don't seem to have, maybe like they don't have an alphabet language, yeah? What's their alphabet? How many letters, you know? What are their word processors like? How do the dolphins do it? And there's some neat ideas on that. And the way the dolphins do it goes something like this, it's speculated. What the dolphin does, the dolphin swimming over a nice great big terrain and big valley down there, all nice stuff down there, dolphin goes, come back in. So that come in is the image that the dolphin has, yeah? And with that image, that dolphin has then a view of that world, yeah? Now the dolphin goes to some friend and goes, and puts that image directly in the mind of the friend. No language needed, gang. Maybe the dolphin embellishes a little bit, lies a little bit, like, you know? Don't we do that when we're cutting music, right? I mean, little mistake we cut in here or there, or embellish this frequency, or cut that one down. Maybe the dolphin does that too. Maybe the dolphin hears and goes, and a person says, no way, honey. How do they say no way, honey? I don't know. But little blips. Kind of neat that the dolphin at least can communicate its environment with the same sense that it receives it, yeah? We can't do that. So who's better off?
Us.
We got things. You know what separates us from the dolphins? Fingers. Maybe not mine. fingers. We get fingers. We can do things. Isn't that nice? How can a dolphin type, you know? Would you expect sound to travel faster in warm air or cold air? Or make no difference? From what you guys know about the theory of matter, warm air means the molecules, cold air means the molecules, yeah? What kind of air do you think you can get one molecule tapping the next, the next, the next? By the way, you know how sound travels, don't you? When I strike the tuning fork, it vibrates back and forth. Doesn't it hit a molecule, another molecule hit another, another, and doesn't that cascade through? Picture the whole room with ping pong balls right now. I take a big paddle, and I, boom. Wouldn't those balls hit one another? Dun, dun, dun. Now, one ball here doesn't fly across the room. When I speak to you and go, hello, it's not like the molecule come right across the your ears. Oh, my gunman. That doesn't happen, does it? What happens when I say hello? I just, all the molecules start moving. Like the ping pong balls go. Can you see them all moving in your mind's eye? How many say, no, I can't picture that. You'd have to show me more. I just can't picture things like... Show of hands. Okay. No, that's what happened. So anyway, what do you think? Warm air or cold air communicate the sound faster? Check your neighbor. How many be saying, I think the sound would travel a little bit faster in the warm air? How many say, nope, that makes sense, but you wouldn't have asked the question if it made sense. You asked the question because it was the opposite. I think sound probably travels faster in the cold air. How many say, no, I think the speed of sound has nothing to do with the air molecules moving. It's just 340 meters per second. If you don't believe it, here it is right here. Well, it turns out, gang, if the air molecules are already jiggling faster, then they'll tap the neighbor all the quicker. And so the faster moving air molecules will send sound a little bit faster than slow moving air molecules. So the speed of sound depends upon the temperature of the air. Okay? And your book gives the value as to how much it increases per degree or something like that. I can't remember the darn thing, but you get it in there, yeah? Question?
If it moves more quickly in air where the molecules are moving more, when we talk about a movement in a solid or a liquid, which obviously the molecules are not moving as much, how does that compare between the two?
That's a very good point, Dave. How the sound travels has to do with something I haven't even talked about. A lot of people think it has to do with the density. That if something's very, very dense, sound will travel very, very quickly through it. Like a piece of putty is very dense. Or a piece of lead is very dense. Would you expect sound to travel very well in a lead pipe or a steel pipe? If I bounce the lead pipe and bounce the steel pipe off the floor, if I drop the two, which would bounce off the floor, the lead pipe or the steel pipe? The steel pipe. It turns out that the speed of sound has to do with the elasticity of the substance. When you deform something, how quickly will it snap back? And steel is very, very elastic. So sound travels very nicely through steel, but it's not as dense as lead. And even the density of the air falls out. It doesn't have to do with the density of the air or the density of the medium. It has to do with the elasticity of the medium, and then a second order effect is, as we're talking right now, the temperature of the medium. Rest assured, sound will travel a little faster in a warm day than a cold day. And let me give you some evidence of that. It's something that occurred to me when I was a kid. I couldn't figure it out. And later on, when I got into physics, boom, the answer to my question came. When I was a kid, I used to be a Boy Scout. And we used to go camping up at Camp Nye in Saugus, Massachusetts. And we'd camp on one side of the lake. This is a lake. And there'd be another scout troop over here. And we'd have our tent set up here. And we'd tent out here, you know. There's our troop here. Here's that troop over here. They've got their tents. Okay. In the daytime, you could yell over to these guys, hey, you guys, how you doing? And they say, speak a little louder, I can't hear you. How you doing? Fine, how you doing? Oh, okay. How's it going? Oh, you know how these heavy conversations you have, yeah? But it turns out we could just barely hear each other. But at nighttime, you could hear these guys whispering in the tents. You could hear them so clearly. I can remember that, and I wonder, wow, at nighttime I can hear those guys. How come I can hear them so good at nighttime? In daytime I can't. And I didn't know the answer to that. And it took me a long time to find the answer to that. Has anyone ever experienced something like that? It's not all the time true, but under special conditions, sometimes you can hear a lot clearer over a long distance than other times. Let me tell you what happened, okay? It turns out that over here, let's suppose over here, someone says, hello, how are you? And we get sound waves coming off like this. And the sound keeps going. Now it turns out the direction of sound will always be at right angles to the waves. So for example, like this, it's like that. And up here it's right angle, right angle, right angle. See that? So when all the air has the same temperature, then the sound will travel at equal speeds in all directions and form all these circles, yeah? But how about in the case where maybe at nighttime it's relatively cool above the water and relatively warm up above, a so-called temperature inversion. When that happens, how about this wave? Will this wave get to here, or will it be further along? In the warm air, it would get to here. In the cold air, it would get to here. And up here, maybe up to here. So you know what's going to happen to the wave, gang? The wave is going to be bent more like that. And when it gets over here like this. Now, my rays, being perpendicular, up here, ooh, look at that. See that? And maybe up here, and down here. And it turns out if you have a bigger ear, you can hear better. When your friends are far away, does it really help to put your hand like that? Does it? Yes, it does, okay? Ask a rabbit. What's a rabbit doing all the time, right? Okay. Yeah, the bigger the ears, the better you can hear. Does it help to go like this? Hello, you guys! Yeah, it does too. You have to just like a megaphone, yeah? For the ear, too. Okay. So what you're doing is you're getting more energy in the ear at nighttime than you are in the day, because the sound is being bent. The waves are being bent. We don't say waves bend because one part's going faster than another. We have a name for that. What's it called, gang? Refraction. We say the wave is refracted. One part's going faster than the other because of a speed change. What underlies the phenomenon of refraction? Some people say, well, you got to have a speed change there somewhere. What do you say? Begin with Y, end with P. Try it. Yep. And that's true. So refraction is a change in the direction of a wave by virtue of a speed change. Refraction.
Sound refracts like this. Does that have something to do with refraction of light?
It turns out that anything that we call a wave will exhibit the properties of waves. And one of those properties is refraction. And here I'm talking about sound refracts. Guess what we're going to talk about later, gang? Light refracts, okay. We talked about sound interference. Later on we'll talk about light interference. We talk about light interference, we'll find out that's why you get the pretty colors on gasoline spilled in a wet street, you know? And the sound interference, by the way, my cousin is deaf in one ear. He can't hear in one ear. And you know why he can't hear in one ear? Because he spent many years with a jackhammer. That's loud sound. You know how tomorrow's jackhammers are going to be, gang? Tomorrow's jackhammers, you know the sound they make, yeah? I see people out here on campus last semester doing those things with no earplugs. Yeah, I don't need any earplugs, man. I don't need You do need earplugs, honey. My cousin's deaf. That sound. Shake. Tomorrow's, gang. You know what tomorrow's jackhammers are doing? They're developing them right now. Tomorrow's jackhammers broadcast the sound to your ears, but exactly out of phase. So when a high pressure hits your ear, you get broadcast a low pressure, and guess what one does to the other? cancels it out. So the guy with a jackhammer tomorrow, you're going down the street and you hear this noise, and you see these two guys like this just chatting with each other. You know what? Everything, all the jackhammer noise cuts out, but everything else doesn't. They don't hear it. Ain't that neat? Interference of sound. They'll interfere that, and it's nice for the health, too. The eardrum is not going like that anymore either, see? It's come to hand. Nice. Interference. So interference is a property of waves. And refraction and what other things? Oh, reflection, of course. Reflection, like echoes, yeah. Light can be reflected, yeah. So all these properties we're talking about now, vibrations and waves, will, of course, hold with light or any kind of wave. When you see these tuning forks on top of these boards, these are called sounding boards. When I hit the fork vibrates, but the fork is attached to the wood, and it makes the wood vibrate as well. And that makes the sound more intense. I think you can see when I put it toward you, the sound will go up. I'll pass it by the microphone in my chest. Watch. You guys all hear that more, did you? No, not from your frame of reference, okay? But right now? So it's like the megaphone over here. The sound is coming out like that. Huh? Here's a little tune. Here's a little music box. Be hearing? Want to be hearing better? A little better, gang? Yeah. You like? What we're doing is we're forcing the wood to vibrate. That's a forced vibration. Could you guys remember that? When you force something to vibrate, that's an example of forced vibrations. Ain't that neat? Huh? Okay. But sometimes you can make things vibrate in the direction in which they would... how do I cut this off? We'll have a little vibrations as we continue, gang. Sometimes you can get the vibrations matched to an object's natural frequency. Because it turns out that everything will vibrate at its own frequency. And once in a while, you can set something vibrating without touching it. And when that happens, we don't call it refraction. Guess what we call it, gang? It begins with an R nonetheless. Resonance. Let me show you an example of resonance. There's a couple of tuning forks. I've got these tuning forks so that they're the same frequency. I think they're 256. Yeah, 256, musical note C. Yeah? Okay. What I'm going to do is I'm going to strike one fork, and you listen. Hear that? Now you guys think, oh, he really struck that one too. No, I didn't do it. Why don't we try it again? Watch. No, I can't resist horsing around. You get the idea. I strike this one, what? Either hand. Ain't that neat? Huh? The wonders of science. Yay, all right? We call that resonance, gang. Resonance. Now, HC. How come this resonated? We can understand resonance if we think small. This is something you can really understand. Watch. I'm going to strike this. These things are flat back and forth, yeah? Flaps back and forth. Isn't it like that ping pong ball hitting the balls, right? It slows things up back and forth too, yeah? And those that we have, whoop, don't they hit here?
Yep.
Do you believe that little pitter-patters of molecules could bend hard steel?
Yep.
How many say, oh, no, that could never happen. Come on, I can set this thing vibrating with those little molecules, yeah?
Yep.
Okay, here we go. I hit this, boom. Boom. Now, let's slow it down. High pressure hits this prong, yeah? Bends it, right? Okay, now what follows the high pressure?
Overshoot.
So what it does, it swings back to where it started, overshoots, over here, and right to here, and what happens right then? Right then. Bam! You see why the timing is important? At that particular instant, the next train comes in. Boom! But now it's already moving. So it goes a little further. So, boom. Now what's it swing into again? The vacuous region, right? The rarefaction. Boom. And when it gets right here, right here, right here, right then, what happens? Boom! You see the next one. Boom. 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 So it's not how hard you push, it's the rhythm with which you push that counts. Do you see that? And if these are both the same frequency, you ever hear people talk about, oh, so-and-so's on my wavelength? They're kind of talking about that, see? If you have the same wave, same frequencies, then this one will set this into resonance. A couple of years ago, it must be 5 years ago now, I was skating through Golden Gate Park. I roller skate. And I'm skating through Golden Gate Park, and there's a kid, Saturday morning, this kid sitting on a swing all by himself, and the kid says, "Hey, mister, give me a push." I look and I see all the wet, soggy grass between me and him, and I got to clank through all the grass, get my ball bearings all wet and everything. You know, I says, "Oh, what'd you say, kid? You heard me. Come over here and give me a push." You know how some of the kids are today? The kid didn't say, "I know you're busy and I'm busy, one human being to another. I'd be ever so delighted if you would come over and take a little time off and give me a little push." Interaction between human types, huh, brother? There was no tone of that in his voice at all. And I said to the little kid, "I'll give you a push." And I clanked through the grass. And here's a little kid sitting there on a swing like that, right? And he sees the look of terror in my eye. And the little kid says, "Oh, don't push me too hard." I said, "I won't push you too hard." He said, "I'll push you nice and easy, okay?" So again, it's not how hard you push. It's what? It's the rhythm with which you push. And if you push right in rhythm, you can set up a very, very nice amplitude. See? A large amplitude, and that's what resonance is all about. Pushes at the right time. I used to have an old car. My God, it was a 54 Plymouth. And that 54 Plymouth had a loose front end. And it turned out at 30 miles an hour, gang, the frequency of the wheels lobbing at 30 miles an hour happened to correspond to the frequency of the whole front end.
Bye-bye.
So you're driving the car 28, 29, 30, 31's okay. They say, "Well, how come that one speed, honey? How come that one speed, a magic speed?" It's no magic speed. You guys see it? See why? When you get the frequencies matched. One time I walk in a store, I see these glass shelves and all these radios on there. And what happened was when the notes from the radio would get to a certain pitch, the whole thing would vibrate. Then go down, the whole thing vibrate. You guys know what's going on? Resonance, see? I was matching the frequency of the shelf. Because everything will vibrate at some frequency. And when that frequency is matched, you can get things to resonate. This happened tragically some time ago. It was in Dallas, Texas, some big hotel. All the people at the top were going, "Yay, yay, yay," and all bouncing up and down. And guess what the resonant frequency of the structure was? Yay, yay, yay. Boom, down it comes. Yeah. You know when people cross bridges? Military types going across a bridge. Before they hit the bridge, the honcho's going, "Hut, hut, hey, hut, 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 hey, four," or step, 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 step. But when they get to the bridge, they break step, and then like that. And then maybe everyone crosses the bridge out of step. Why? What if the resonant frequency of the bridge is hut, hut, hey, hut? You know what I'm saying? In fact, this happened in Manchester, England some years ago. All the troops are following the honcho, and the honcho's counting cadence, and he goes across, hut, 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 and he's ahead, and he keeps going. He's on the other side of the bridge, so hut, 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 and the people wipe out city. You guys know about the Golden Gate Bridge in New York, I guess. How the Golden Gate Bridge is got the same resonant. Yeah, they really screwed up in this, man. It's talk about the disaster of the earthquakes. The Golden Gate, the George Washington Bridge. George Washington Bridge. You guys be knowing the George Washington Bridge has a resonant frequency that's equal to that of a cat's trot. You guys know about that? Cat, yeah, medium-sized cat. Who's from New York City? They can back me up on this. You want to walk across the George Washington Bridge, they get a little cat guard, a little sign, "No cats." Now, a lot of people think that's cute and that's a joke, but come on, you physics types, we know what, right? You know why? You know how a cat runs, by the way. You get a cat running. Blip, 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 blip. 20 minutes later, blip, 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 blip. Beautiful timing. How about a dog? Blah, 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 blah. All in minutes. No, don't count. But the cats, honey. Guess what they found out that the natural frequency of the George Washington Bridge is? So what would happen if you let a cat run across that bridge? You know, you guys, you noticed when I hit this that these air molecules bent the steel. You had evidence of that. You heard it, right? So, oh, well, maybe little air molecules can bend steel, but not a cat. How about it, gang? You know what happened? That cat went across that bridge, blip, 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 blip. In World War II, that's why they up there all the time looking for cats. There might be some, there might be some spy, little cat going, take our whole bridge down, man.
Can't they build some kind of damper or something?
Oh, no, there's no way to protect against the cats, Paul. No, we're at the victim of cats. I'm not going to... I think, you know, I woke up in a dream recently. I woke up in a dream, and I dreamed I was going across that bridge, and I had the, you know, that stones on the radio and everything going. And all of a sudden, looked down in my dream, and I saw a cat running right beside me. I mean, talk about waking up in a cold sweat. Could you imagine? What could be a more horrible thing to be right in the middle of the George Washington Bridge and seeing a cat run beside you, right? I'm talking about those calico color jobs, the 3 color jobs. You know what I'm talking about? Okay? Bring that whole bridge right down. Would you like to see a movie of a cat that brings the bridge down?
Yes.
Some of you guys thinking, oh, you're horsing around. You're not being serious. Let me ask you a question. Am I the type of person who would not be serious with you? Would you like to see a movie of the catastrophic collapse of such a bridge by a cat? Yeah. 9-pound calico colored cat? Okay.
Well, let's see that movie right now. Here's a similar bridge in the state of construction. And it's the Tacoma Narrow Bridge in the state of Washington. Look at the size of those girders. Very strong. Steel. And here we are on opening day. What were you guys doing in 1940? And here we have dignitaries coming across the bridge, opening day. Look at the strength of that bridge, big steel girders, concrete pavement, a mighty bridge, very strong bridge. But one thing, very elastic. And here you see some of the evidence of that elasticity. Turns out the bridge undulated. They called it galloping Gertie. Especially in the wind, it would kind of move around a little bit. Look at these vibrations. Evidence of the elasticity of steel and even the concrete pavement. People come on over the bridge. Some were reluctant to do that, and they took alternate routes. Galloping Gertie. Whoop, look at this, look at this. A slight gale one day. Whoop, I shouldn't say gale. When the cat was released on this bridge one day, look what happens here. There's an evidence of resonance. See those bushes moving around a little bit of wind there, but let's stick to our cat theme. And there it goes. Look at that. This is in real time, gang. Scout's honor. This is not time lapse or speed it up. These are the real vibrations, real time. That bridge is resonating. What's the cause of that resonance? That calico-colored cat. They sent a fellow out there to kick the cat off the bridge, but the animal rights activist said, no, let the cat do its own thing. Every creature has a right to do its own thing. If you look very carefully, in the middle of the picture, you can see the cat. The cat's purring, making its paws go up and down, generating this terrible, terrible event. Turns out this bridge was inadvertently uninsured. Turns out the insurance premiums were unpaid by a city official. And that turned out to be a disaster financially for the city, as we'll see very soon. Do you really believe that a cat's generating this, gang? There's a cat. You can see it on the side there. A little close-up view. But better, take a look at your book. Maybe the truth is in there. Oh, There it goes, there it goes. Disaster, disaster. Elastic things have their breaking point. And there we see the collapse of the bridge itself.